Deep neural networks perform astonishingly, yet their decision-making process often feels like magic, an opaque black box. This lack of transparency is a critical hurdle, especially when deploying AI in high-stakes domains like healthcare or autonomous driving. Explainable AI, or XAI, seeks to open this box, to illuminate precisely why an AI made a particular prediction. Among the most impactful Python-powered techniques for computer vision models is Grad-CAM gradient-weighted class activation mapping. Grad-CAM operates by leveraging the gradients of a target concept flowing into the final convolutional layer of a convolutional neural network. It doesn't just tell us where something is, it tells us what pixels significantly influence the network's decision for a specific class. The core mechanic involves backpropagating the gradient of the target class score with respect to the feature maps of the last convolutional layer. These gradients are then globally averaged to derive neuron importance weights. These weights are subsequently multiplied by the forward activation maps and passed through a ReLU function, generating a coarse but highly interpretable localization heatmap. Consider its application in medical imaging. A deep learning model might classify an X-ray as indicative of pneumonia. Clinicians need more than a label, they need to see which region of the lung prompted that diagnosis. Grad-CAM visually highlights these critical areas on the original image, fostering trust and enabling informed human oversight. Traditional saliency maps, for instance, often highlight noisy edges or high-contrast pixels without direct class-discriminative relevance. Model-agnostic methods like LIME or SHAP provide local explanations, but can be computationally intensive and abstract from the model's internal feature hierarchy. Grad-CAM, however, directly taps into the CNN's learned representations, offering a visually intuitive class-specific explanation with minimal overhead. It is important to note, however, that Grad-CAM's resolution is inherently limited by the spatial dimensions of the final convolutional feature maps. This means while it excels at localization, it might occasionally miss minute yet crucial fine-grained details within a broad region. This limitation has spurred further research leading to enhancements like Grad-CAM, which refine the weighting of positive gradients to achieve sharper localization, particularly for multiple object instances. The trend indicates a shift towards integrating these gradient-based insights with transformer architectures, creating even more robust and granular XAI methods. Ultimately, explainability isn't merely a debugging tool, it is foundational for building reliable, ethical, and trustworthy AI systems. Techniques like Grad-CAM transform opaque predictions into transparent, actionable insights, evolving AI from a mysterious oracle to a collaborative, understandable partner.